All right. All right. So I think I may have mentioned this in passing yesterday, but here, I want to emphasize this, that there's two main categories of electricity. It's what's called direct current versus alternating current, right? Now, if you have anything battery operated, I bet you guys have a bunch of battery operated appliances just within reach, right? You guys got those handheld calculators on your desk. I bet you guys have cell phones in your pockets, right? You guys got maybe a wristwatch, possibly, right? Those are all battery operated, and for anything that's battery operated, it's called direct current. There's direct flow from, well, terminal to terminal. Now, if you were to watch electrons flow, do you guys think the electrons actually go from the negative terminal to the positive terminal, right? But guys, look at this animation. Look real close. Do you guys see that the red dots are actually flowing from the positive to the negative side? That's opposite of what the electrons are doing. What's up with that? So the history behind that is, if you go back to like Ben Franklin days, back in the 1700s, they didn't know the structure of atoms, or that it was actually moving electrons that was electricity, right? So they just did a coin flip, and they defined electric current as the flow of positive charge, which is what this animation is showing. It's showing the flow of positive charge, right? Which again is the opposite of what the electrons are individually doing, which is flowing in the opposite direction, right? But it doesn't matter mathematically if you define electricity as the flow of positive or negative current, right? Either way, mathematically, you get the same voltage drops and the same current in amps. So it's mathematically equivalent. So we have this kind of backwards convention that's just kind of stuck in the textbooks, and we just throw with that. So it's okay. Yeah. Right. Just a side thought, not really consequential mathematically, though. Right. All right. And then, okay, what's the deal with alternating current? Here, a little bit of history. Do you guys know what are the current wars from the 1890s? The current wars. Right. Does anybody know? You guys have heard of Thomas Edison versus Nikola Tesla, right? So here, back in the 1890s, electricity, people were realizing, okay, this is useful. We can come up with these electric appliances, and wow, if only we had some kind of like central power plant and an electric grid where we could like sell this electricity to a bunch of individual homes, right? But we need some way to distribute that electricity, and these were the two options they're looking at right here. Now, I guess alternating current, there's no net movement of well, you could think of those as electrons. It's the same idea, right? So the electrons slosh back and forth, but there's no net movement. There is a frequency, right, of sloshing back and forth, right? So that's true, right? All right. And so for the history side of this is Thomas Edison had a bunch of patents related to direct current. So he was a proponent of that because he had all the patents, right? And then Nikola Tesla had a different idea. He said, well, let's have a rotating magnet that oscillates the fields back and forth. And that eventually won out. And that's actually what we use today for electric grids, is alternating current. And the advantage of alternating current is that you can very easily step up and step down voltages. Therefore, you can transmit electricity with high voltages and low currents. And you can transmit it a lot more energy efficiently that way, right? Like, guys, do you see a poster up here that says Joule's Law? Guys, everybody look up at these posters. Do you guys see one that says Joule's Law? And one of the lines says P equals IV. Do you guys see that one? P equals IV. So P, power, okay, that's in watts. Okay, so great. Power plant has to submit probably some number of megawatts to like an entire community, right? So a lot of watts are going out, but that I is ideally small, right? You don't have a lot of current flowing. But the only way to do that is to pump up that V, that voltage, to like thousands of volts. And then you can use what's called a transformer, we'll talk about in a couple of weeks, to step, in this case, step down the voltage from like thousands of watts down to, do you guys remember yesterday what I said, what was the alternating current voltage standard in the States? It's like 120 volts, 120 volts, right? One more thing with alternating current is sloshing back and forth with some frequency. Does anybody know? Because everybody has to be on the same frequency standard, otherwise the appliances wouldn't work, right? Great. I want to go to the store and buy an appliance and make sure that it, I get home and I know it works, right? Does anybody know what is the alternating current frequency standard in the United States? 60 hertz. There you go, 60 hertz. Yeah. And then, yeah, Europe is on a 50 hertz standard. And there are different standards depending. Like I think ships have some unique standards. I think planes, right? But yeah, these outlets right in this room, 60 hertz standard is what we're looking at. All right, so there you go. There's a little bit of trivia, but I think it's worth knowing. Yeah.
If I got the European watch plugged in here, it wouldn't work for because it's
true. Yeah, guys. If you go to Europe and you buy a European appliance and bring it back to the States, yeah, it's probably not going to work because they're on double the voltage that we are, and yeah, a different frequency standard, right? Yeah, for both those reasons. Now, actually, I should say, something like a washing machine, I think might actually be on a double voltage standard. Like some of the bigger appliances, like dryers and washers, I think actually are on like 240 volts, or they're like special, right? But they would be on a different frequency, so for that reason, it wouldn't work. Yeah. Yeah. For you, yeah. Although, you know, since I got an adapter right in front of me, let's take a look at this, because this adapter might be universal. Although there's a bunch of little details too, like these prongs might not possibly fit different outlets around the world, right? But you guys see this says what's the input and what's the output here. So this particular charger will take input anywhere between 100 and 240 volts, which is pretty much the entire world standard. And does it mention frequency? Well, sometimes they'll mention a frequency standard too, and they'll take either 50 or 60 hertz usually, right? This one doesn't mention it, but this will output 5 volts DC, right? Which again, I was talking about yesterday, right? It's safe to, I can just cut the leads on the other end, and even if I have this plug this in, right, it's not going to shock me. It's going to be just 5 volts. Okay. Right? All right. All right. So you guys see this page in front of you. This page. I'm going to do some of these examples with you guys, and then right, we're going to take the rest of class and help the guys out as much as I can here. All right. So the top half of this circuits page is just saying what's the equivalent resistance for the entire circuit, right? And I throw in different resistors, and I told you how much resistance they each individually are in ohms, right? Do you guys see on the left side is a couple of parallel lines, one longer than the other? That represents your voltage source, right? It might be this charger, might be like a battery. I know I have a 9 volt around here. Oh, here you go. 9. All right. Boom. There's all right. So that's these 2 lines, one longer than the other. Could be some kind of voltage source, like plug that in, something like that, right? Right. And this voltage source like feels like it's pushing against effectively one equivalent resistance. And that's the question is, well, what is that equivalent resistance, right? So number one. Now number one, there's only one resistor. See that little jaggedy line labeled R1, right? And I told you what it is. Now, all of us have different numbers, right? But we all got the same geometries, right? So mine says 9 ohms. Therefore, that's the answer, right? Is just 9 ohms. Right? Okay. So you guys see the answer to your number one. Right. Now number 2. Now there's 2 resistors. So my paper says 2 ohms and 4 ohms, right? But it depends how they're wired up. Are they in series or parallel? Because that'll make a difference. So if you start at the voltage source and you're tracing around the circuit, you guys see how all the current has to go through this resistor followed by this resistor sequentially, right? The traffic analogy is if you start in this parking garage and you drive around town, you have to go through that stoplight and also that stoplight sequentially, right? And if there's like a line of 100 cars, all the cars have to go through all the stoplights. Is that series or parallel? That's series. Yeah, series. If it's all sequential like that, one after another, that's series. Okay. In series, how does series work? Can I just very simply add those numbers together? Yeah. So in my case, 2 ohms plus 4 ohms makes 6 ohms. Boom, done. Okay. All right, you guys can do series, just add them together. Right, just like we did yesterday. Right. Number 3. Does number 3 look like 3 resistors all also in series? Do you think? Can you basically do what we just did, but for 3? Did you see that? Right. Number 4. We're back to 2 resistors, but are those in series or parallel? Parallel, right? Here's one way you know if it's parallel is if you start the voltage source and start tracing around, like tracing the current around, current's going around, it hits this junction and it splits. The current's going to split. Part of it splits left, part of it splits right. It's going to split. Right? If you were traffic driving around, you'd have an option which stoplights you want to go through. Right? It's pushed through both resistors simultaneously. That's parallel. Now, parallel, mathematically, can you treat that like 2 guys painting a fence? Yeah, and then the more team members you have, the less time it takes to paint the fence. Let's say the more and more resistors you add in parallel actually decreases the total resistance. It makes it easier to like drive around town, right? You've got more options, more streets you can drive on, right? So if I have 3 ohms and 4 ohms, before I go plugging and chugging, let me get kind of I'm going to guess, right? Well, if it took this guy 3 hours to paint a fence and this guy 4 hours to paint a fence, and they make a team. Actually, we did do this one yesterday. Right? That was exactly my example, wasn't it? wasn't it like 1.71 hours it took, I think, to paint the fence, right? I bet this is going to come out to 1.71 ohms, right? And I'll remind you guys the two ways that you can do this. You can use the fraction method or the product over sum method. So the fraction method is you go 1 over the total, which we're solving for, is 1 over the first resistor plus 1 over the second resistor. Right, solve it that way. Right. So break out a calculator. Right. So 1 over 3 plus 1 over 4. Right. So 1 over the total, resistance total is, I'm getting some crazy decimal, 1 over ohms. Right. So one more step, I have to take the reciprocal. I can do 1 over the answer, right? Or I could hit that key above the 7 says x to the minus 1. That'll also take the reciprocal, right? So there it is, right? Resistance total is 1.71. That's ohms of resistance. That's Greek letter omega for ohms. Okay. Right, which is an answer on my paper. So I'll circle that and good to go. Yep.
On that one, it's the process you were just doing.
Yep.
Where did you get the 1.71 out of the 5.23?
Take the reciprocal, because 1 over the resistance is 0.58. So you have to take the reciprocal.
Oh, okay.
So do 1 over. Right.
So,
Okay.
So like,
oh, wait, never mind.
Yes. All right. You guys good? All right. All right. And then I said I was going to show you the other way to do this also. So you could just jump straight to the total equivalent resistance is, and you can just do product over sum. So it'd be 3 times 4 over 3 plus 4. This be some number of ohms. Okay. Again, you can only do product over sum for 2 resistors at a time. 12 over 7, but it's same thing as before. Okay. All right. All right. You guys got a number 4? You guys good? Just product over sum, boom, done. All right. Number 5, I just want to mention this verbally. Does that look like 3 resistors in parallel? Do you guys think? Do you think you could treat this like 3 guys painting a fence? Right, you guys can figure that out. 3 guys painting a fence, right? I'll leave that one to you guys. Right. Number 6. Right. Now I have 3 resistors, but it's not straight parallel or series. Right. So I need to introduce a process to you. Actually, I may mention this process the last 5 minutes of yesterday. Right. When you get more complicated circuits, there's a particular process that you have to follow. Right. And it goes like this: you find your voltage source, which in this case is on the left side of the circuit, right? You fly over to the complete opposite side of the circuit and you work your way back towards the source, and then you find equivalent resistances along the way. Okay. Now this one's kind of simple because there's only 3 resistors, but if you have like 100 resistors, okay, you have to do this particular method. And if you do anything else, you're just gonna get nonsensical numbers, right? So what I'm gonna do is say, here, first I'll just draw exactly what I have on my paper, right? So got a voltage source on the left. I have an R3 up here that's listed as 5 ohms on my paper, so I'll label that 5 ohms. Okay. And I got these 2 resistors out here. This one is labeled 2 ohms, and this one is labeled 4 ohms. Okay, so that's my paper. Again, everybody has different numbers. Right? Okay. Are you guys good with the setup? Right. So the process I just told you, I said find your voltage source. I didn't even tell you how many volts it is, but that didn't matter, right, for this question. Fly over to the opposite side. So I'm just going to start with this 4 ohm guy. Work back towards the voltage source, and then I run into this 2 ohm guy. Right. Now, next question is, how are these 2 resistors interacting? Is that series or parallel? Parallel. Right. And I know it's parallel because the current has to split and be pushed through both simultaneously. That's parallel. Can I treat that like 2 guys painting a fence? Maybe product over sum. So the resistance equivalent is product over sum. It's like 8 over 6. It's like 1.33 ohms. Okay. All right. Is that working out for you guys too? With your numbers? You got some number, right? But we're not finished yet, right? I'm going to redraw the circuit. Yeah, this one's kind of simple. It's not crazy, but if you get more complicated circuits, it's a good practice to do what I'm doing, where you just redraw the equivalent circuit. Okay, I still got this resistor up here, haven't touched him yet, this many ohms, right? But these guys collectively, it's as if there's a single resistor that's this many ohms. So I just solved that. Okay. Okay. You guys good? All right, so we're picking up from that part of the story. We're going back towards the voltage source. Then I'm going to obviously run to that resistor. Okay. Now these resistors are in what, series or parallel? Series. Yeah. There's only one street. It's sequential. That's series. Therefore, can I just add them up? Yep, that's it. Right. So now my equivalent circuit looks like this. Right. 5 and 1.3 is like 6.3. Right. It's as if there's only a single resistor on the entire circuit that's that many ohms. Right. And that should be the answer. And make sure that that's an answer choice on the paper. It is. Boom. They're done. Okay. All right, guys up there? All right. Let's do. All right. Let's come down to the bottom half of this page. Right. Right. So we got 6 circuits down here. Yeah, they're looking more complicated. Right. And also, if you look really close, there's a pair of questions for each circuit. Right. Not only what's the equivalent resistance, but the follow-up question is, given the voltage source, what's the current flowing through the circuit? Okay, so we're going to answer both those questions, right? Let's start with number 9 and 10. Now, this circuit's kind of special. This one's unique compared to all the other circuits, right? Right. So let's start with the same process that I was talking about, right? Just find your voltage source on the left side, fly over to the right side of the circuit since it's completely opposite, right? And the first 2 resistors we run into are R2 and R3. Guys, R2 and R3, are those in series or parallel? Series, yeah. Whatever electricity happens to make it to that part of the circuit does have to go through both sequentially. That's series. So can I just add those together? In my case, 3 and 1 is 4. Okay, so something like that. Okay. All right. Then I'm working back towards the voltage source. Ooh. Now here's where we're going to run into something. It's a little bit weird. Right? And this is the only place I did this on this entire paper. Right, guys, this line right here. This is a wire that has no resistor on it. Guys, a wire with no resistor. Is that like 0 resistance? Right? Now let's anthropomorphize this current for a moment. Say this current come around to this part of the circuit, hits this junction, right? Looks to the left and sees a bunch of resistance. Looks to the right, sees 0 resistance. Because if you're a car driving around town, you look to the left, you see a bunch of stoplights. You look to the right, see a completely open road with nothing on it. And you want to get around town in a hurry. Which way are you going to take every single time? Yeah, the open road. That's the path of least resistance. Do you think 100% of the current goes that way? Does any of the current go through R2 and R3 at all? Right. Yes. No, it doesn't. Right. It doesn't. Right. This line right here, this wire has a name. It starts with an SH. It's called a short. It's a short. We just shorted out our R2 and R3. R2 and R3 are not even part of the circuit. I could have made up any numbers there. I could have made 1 ohm and a billion ohms. It wouldn't even matter. You just ignore them. There's your circuit. You guys see that's your entire circuit? Right? Doesn't that look exactly like number 2 that we just did a few minutes ago? Right? So R1 and R4, those are the only resistors part of the circuit. Right? Are those in series or parallel? Series. Can you just very simply add R1 and R4? So for me, 3 ohms and 1 ohm makes 4 ohms. Boom, done. Okay. Okay. Now here's the first follow-up question we have related to the circuit. Is now I'm giving you a voltage. I'm saying 5 volts. Hey, 5 volts. That's the cell phone charger that you guys are gonna get on Thursday for the lab. Right? 5 volts. 5 volts DC. Right. So given 5 volts acting on the resistance I gave you, or that you just solved, what's the current that flows? Well, the current is directly proportional to the voltage and inversely proportional to the resistance. So it's V over R. Right? So let's do that. Write this down on paper. Right? If I got let's do I equals V over R. It's called Ohm's law. Right? And I've got 5 volts acting on 4 ohms. That's like 1.25 amps. Okay, so I got 1.25 amps. which is an answer choice. Boom, done. All right. Can you guys do Ohm's law? All right. Is everybody good?
Yeah.
We're good. All right. All right. Let's do number 17 and 18. So the circuit way over here. Right. Ooh, this one's looking pretty crazy. It's gonna be a fun time right here. So voltage source on the left side. I'm gonna fly over to the right side. Actually, I should just redraw this. Let me go and redraw this. Make this big. It's big here. Right. So number 17 and 18. Right. You guys can see this is gonna be a big old process going on here. Try to this nice on this paper if I can. Right. Got a voltage source here. We got resistor. This and now, okay, so my paper says it's this many ohms. It's probably different on your paper. Okay. This guy up here, I'm looking, my paper says this many ohms. This one down here, I got this many ohms. This resistor here says it's this many ohms. And then, okay, so I just copied down exactly what's on my paper. So remember the process that I just told you guys. Right? Find the voltage source, happens to be on the left side. We 5 volts, that doesn't matter yet, but it'll matter later. Right? I'm gonna fly over to the opposite side of the circuit, which is this resistor, work my way back towards the source. Next, I run into this guy. Okay, so guys, these two resistors right here, is that a series or a parallel relationship? Parallel. You guys said parallel, right? Because I see a junction. I see the current's going to split. We push through both simultaneously. So can I treat that like two guys painting a fence? Okay. 4 hours to paint a fence, 3 hours to paint a fence, make a team. Right. I'm going to guess. Oh, wait, this is an example again. Let's keep showing up over and over again. I know what's going to be. Right. So let's do product over sum. Right. Okay. So it's as if there's a single resistor there that's that many ohms. Okay. All right. Is that working out for you guys too with your numbers? Okay. All right. Then redraw the circuit. So still got my battery here. Okay. Still got this resistor, haven't touched yet. This resistor, haven't touched yet. This resistor, haven't touched yet. And then, well, all this collectively is like this equivalent resistance. Boom. Okay. Here's my equivalent circuit. Okay. Okay. So now working back towards the source, I'm gonna run into these resistors. Now, these 3 resistors right here, are these in series or parallel with each other? Series, because right? Whatever electricity happens to make it to that part of the circuit, not all the current will, but some of it will. Right? Whatever makes it to this branch has to go through all 3 sequentially. It's one-way street. Yeah, that's series. So can I very simply add those up? Just add them up. Okay. So redraw the circuit again. Got my voltage source. Got this resistor I haven't touched yet. Right. And then 1, 1, 3, 5. That many ohms right there. Boom. Okay. So all you do is just add these 3 guys together because they're all in series. Oh, that number right there. Okay. Is there any question where I'm getting any of these numbers? Okay. So working for you guys. All right. Now working back towards the source. Finally, these 2 resistors, is that series or parallel? Parallel, right? Because the current splits, push through both simultaneously, right? If it took this guy about 5 hours, this guy about 5 or 6 hours to paint a fence, I bet together it's going to take somewhere between 2.5 and 3 hours to paint the fence, right? So let's do product over sum and figure out the equivalent resistance for the entire circuit is product over sum of those individual resistors. All right, and that's like, yep, it's exactly kind of what I was estimating. That many ohms. Make sure that's an answer choice on my paper. All right, that was what we just did. Yeah, I got the answer right here, right here. Bam. It's a match. It's all good. All right, guys good? All right. So the follow-up question to that is, well, how much current? Okay, so now we're gonna skip over to Ohm's law. You guys ready for Ohm's law? How much current flows is voltage acting on resistance? Okay. And so I equals V over R. Okay. And I've got 5 volts acting on, see, I just found 2.67 ohms. 2.67 ohms. What is that? Well, it's 5 volts acting on 2.67 ohms. That is 1.87 amps. Okay. Is that an answer choice on my paper? Yes, it is. Bam, right there. All right. You guys doing any good so far? Doing good. All right. So let's flip over to the other side. Okay, so I got 4 circuits set up here. Got some waterfall models set up. I didn't draw the waterfalls yet, right? And some Kirchhoff tables, right? So for this side of the paper, you got to be able to do what we've done so far, right? All those skills we've done so far today are going to apply, right? But we're going to go the extra step of digging down into the circuit. We're going to figure out how exactly is the current flowing each part of the circuit? What's the voltage drop across each resistor, right? We're going to have to break out Kirchhoff rules and friends. That's it. Remember, there's only these 2 Kirchhoff rules, the loop rule and the junction rule, but it threw some others here to complete this, right? So we're gonna do all this, right? I know. At a glance, do you guys see? I gave you guys a straight series setup on number 1, a straight parallel setup on number 4, and then number 2 and number 3 are a little bit more complex. So do as much as we can here. Okay. Also for each one, I gave you some starting values. I gave you guys each resistor, so many ohms, so many ohms, so many ohms. And I also gave you guys a battery, how many volts, right? Like mine says 24 volts, right? Now, once you have that set up, like you know what is the geometry of your circuit and you know what battery it's hooked up to, everything else becomes determinable as to what's the voltage drop at each location, what's the current flowing at each location, and what's the power in watts at each location. Okay, and we're going to figure out the entire table. So kind of like a Sudoku puzzle, right? Once you have the first numbers, everything else becomes determinable, right? So it goes. Okay, right. So what can we do with this, right? Well, maybe I want to turn this into a waterfall, right? Now I do see that all the current has to flow through all 3 sequentially. That's series. What would that look like as a waterfall model, right? Well, there's no branches, right? All it is just 3 waterfalls in a row. Right? So there's splash, waterfall, right? Flow, splash, waterfall, flow, splash, waterfall, right? And then it circulates back to battery, to the pump, gets pumped back up, and round it goes, right? In this waterfall analogy, the height of each waterfall represents the voltage drop. So I'll say delta V, like a voltage drop, right? Do you guys see that there's going to be 3 waterfalls, 3 resistors in series, 3 waterfalls, right? And the sum of the heights of the waterfalls has to match the height of the cliff that's being pumped up in the first place, right? By the way, that's called Kirchhoff's loop rule. So the sum of the voltages in a loop has to go to 0. So it's like 24 volts up and 24 volts down, 24 up, 24 down. Like that. Right? What is the equivalent resistance for the entire circuit? Well, since it's just 3 in series, what do you do with these numbers? Add them up. Yeah. So in my case, 2 plus 8 plus 2, it's like 10, 11, 12. It's like 12 ohms resistance I have, 12 ohms. Okay. Right. Right. Everybody good so far? Right. Then, right, okay, and I gave you the battery, how many volts that is, right? Next column, what is the voltage drop across each individual resistor? Okay, now here's what we haven't done quite yet in this class, but we're about to, is we're going to dig into the circuit to figure out individually what's going on. Okay. We need to follow this rule right here. This rule says that for a series setup, and this is series, so refer to this one, right? The voltage drop across each individual resistor is very simply proportional to that resistor. That's it, right? So if resistor A was like 1 ohm and resistor B was 2 ohms, we say, well, 1 over 1 plus 2, that'd be like a third. A third of the total current drop happens across A, and 2 out of 1 plus 2, so 2/3 happens across B, right? Okay, so something like that. Right. So let's apply it here. I know that there's 12 ohms total on this entire branch, and 2 of those 12 ohms is resistor C, and the total volts supplied by the battery is 24. Right? So I can say the voltage drop across C is, resistor C is 2 ohms out of 12 ohms on the whole branch, so 2 out of 12 times, so 2 out of 12 is the ratio, right? And the voltage applied to begin with was 24 volts. Okay. 2/12 to 24. Right. Guys, what is 2/12 to 24? What is that? 4 volts. That's this number right here. Bam, 4 volts. Okay. By the way, see how I'm getting all whole numbers, right? On your paper, you should either be getting whole numbers, or there might be a version that has like something 0.5. No, I get like 1.5 somewhere, right? But other than that, right? You shouldn't be getting like crazy decimals. Okay. Next one, the voltage drop across B is, okay, well, I see that's 8 ohms right there. There's 12 ohms on that branch. And then, so that's my ratio, and then 24 volts total. Guys, what is 8/12 of 24? 16 volts. So 16 volts drop there. Okay. Then resistor A. So delta VA is, okay, well, that's 2 ohms on A, 12 ohms on the branch, and then 24 volts total. We're back to 4 volts drop. So 4 volts. Bam, bam, bam. Now, how do the numbers in the table we just found match up with that picture? I want you guys to see that it all matches up. Right? Well, I've got 4 volts drop there, 16 volts drop there, 4 volts drop there. Guys, what's my total voltage drop? What's 4 plus 16 plus 4? 24. 24 volts drop. So it's like the heights of these 3 waterfalls collectively is like 24 units, 24 volts, right? And look at that. The battery also pumps up 24 volts, right? That's the loop rule. That's the loop rule right there. 24 volts up, 24 volts down. Boom, boom. Right, you guys see the loop rule in play right here? All right. Next column, what's the current in amps? Hey, this sounds like a job for Ohm's law. Ohm's law. What's the current flowing? It's voltage divided by resistance. You know, you could do this for the whole circuit, or you could do this for individual resistors. Either way, it's going to work. Right? V over R. So all you have to do is divide the previous 2 columns. So do this V divided by this R. Guys, what is 4 volts acting on 2 ohms? 2 amps, right? Right, just put something on paper. Here, maybe put the next one on paper. So we're doing Ohm's law. I goes V over R. Right. So what is 16 volts drop acting on 8 ohms? Is that 2 amps also? 2 amps? Also 2 amps, right? What is 4 volts acting on 2 ohms? 2 amps, right? What about from the point of view of the battery? Battery is 24 volts. It's pushing against 12 ohms total. What's 24 on 12? 2 amps, right? Right? Is that? Do you guys notice that all the numbers in that column are the same? Right? Now that'll always be true for a series setup. In fact, that's exactly what I say on this cell right here. Yes, for a series setup, the current is the same everywhere. Right? You guys should be getting that too. Right? Now, of course, you guys have different numbers than I do, but you should have this. Whatever number you have is like copy pasted all the way down. You guys also have that? Right? You guys good? Right. Last column. What's the power in watts? So we need to break out Joule's law. And we got 3 different versions of that, right? So boom, boom, boom. Let's try all of them, see what happens. So I could go power is current times voltage. I could do that. Let's see that one. Right, that would just be multiplying the previous two columns. So I could do power is current times voltage. So I have 2 amps and 4 volts. Is that like 8 watts? 8 watts. All right, so put 8 right here for 8 watts. Right. Next one. Oh, before I go on, could power also be V squared over R, or power could be I squared times R? Right. Those are the other 2 versions of Joule's law. Right. Let's just see if does that work out. Right. Because what is 4 squared? 16 divided by 2 is also 8. Hey, it worked. Okay. What is 2 amps squared? It's 4 times 2. Hey, that's also 8 watts. So there you go. So all these lead to 8 watts. 8 watts, 8 watts, 8 watts. Check, check, check. It's all the same thing. Okay. Next row. Let's just do P equals IV. Power is current times voltage. What is 2 amps times 16 volts? 32 watts. Resistor A. What is 2 amps times 4 volts? 8 watts. What that would be? Right? Good. Right. Okay, so now pause right here. That's how many watts of power are being demanded by each individual resistor. Right? So 8 watts, 32 watts, 8 watts, right? Guys, how much total power is being demanded in my circuit? What? Yeah, 48. You guys see 48 watts total is being demanded, right? I sure hope that the battery is supplying 48 watts to meet the 48 watts demand, like supply and demand, right? Let's see if it is. So at the point of the battery, what is 2 amps times 24 volts? 48 watts. So there's 2 different ways to get that last cell. You could say, you could just apply Joule's law at the point of the battery. So 2 times 24 is 48, right? So 48 watts, right? Or you could say, does electricity supply match electricity demand? So all the collective electricity demanded has to be supplied. In this case, it's a match. It's also at 48 watts. Okay. All right, guys, get that too? Okay, everybody good? All right. Well, I guess we got about a minute till the bell. Is that a good pause point right there? You guys think? Right. Okay, so guys, tomorrow I'll give you guys all class, which is like 28 minutes to work on this. You guys can help each other out. You guys can ask me if you have any question. I might help you guys out a little bit too, because number 2 is a little bit complicated. But yeah, that'll be tomorrow's plan. Then Thursday will be a lab day.